Hey. All right. If a piece of wire has a length of 1.44 meters, has a current of 2.78, if the wire is placed 58 degrees to the magnetic field with a strength of 5 Tesla, what is the magnetic force it's experiencing? So here we're not told much direction of it, but I'm just going to draw a picture to help visualize. So if this is my magnetic field, and the wire is placed not perpendicular to it, so it's told that it's 56 degrees, I need to find what L perpendicular is. Oops, not LT. L in order to solve for it first, okay? So I'm told this L is equal to 1.44. So I can solve for L perpendicular using my trig functions. So if L is equal to 1.44 meters, then L perpendicular will be sine 56 degrees multiplied by 1.44. So L perpendicular is 1.193, etc. I know my I is 2.78 amps. B is 5.0 Tesla, and FM is my question. So I can put it straight into my formula of I times L perpendicular times B. So FM is 16.5827 newtons. Sig dig 16.6. Not the same? You got what?
16.59.
Did you include all of this? Yeah? Oh, okay. Maybe I'll have to check my calculations. Okay, so next, I forgot to write this in, but you needed one extra thing in this diagram here. So here to here, you're given the length of 2.5 centimeters, and the length of the whole wire is 15 centimeters. Okay, so that's just some additional information that we need for this. Okay, so the magnetic field strength between the horseshoe magnet is 0.335 Tesla. What is the magnetic force acting on the conducting wire when a current of 2.65 amps is running through the wire? So FM is L perpendicular times I times B. So what are we missing? Well, our L is from our picture, but which length do I use?
What does the 2.5 even represent?
The 2.5 is this this amount of wire. Like if this was a if this was the magnet, this wire is a certain length, and then I was told the length that's right in there. So should I use 15 or 2.5? or 15 minus 2.5, or 2.5 times 2 times 15. Just making stuff up now. What length do you use?
15.
Why?
It's all the way.
Okay.
It's going, the current's going through the whole thing.
Okay, the current's going through the whole thing. Let's go back to our,
Can't you only use 2.5 since the only part that's perpendicular?
yes, we can only use 2.5 because it's the only point that's perpendicular. So if we read our definition here, L is the length of the conducting wire in and perpendicular to the magnetic field. Okay, so that was our initial. So you might want to kind of circle, highlight that for yourself here. In and perpendicular. So the length of the wire needs to be inside and perpendicular to the magnetic field because it's that amount of current or that length of current that is actually experiencing that field. So our L we use is 2.5 centimeters. Divide by 100 to get that into meters. So 0.025 meters times by 2.65 amps times by 0.5 Tesla. So FM then is 0.02219 newtons. And so to sig digs, we need 3, so you can put it into scientific notation if you want to. And we need to put direction on here. So which way is the arrow, or is the wire going to be forced? So if the current, so let's look at the current, how it's actually flowing. This is the negative end. So the electrons are flowing this way. So it, because it's the small thing, so like on a battery, this is always negative.
But both of those lines are the same.
They're exactly the same.
No, they're not. This is way smaller.
No. No. Totally the same.
No, the smaller block to the line, there's 2 batteries.
This is a line, this shows
Oh.
negative, this
This
shows
was
positive.
mine. This
Oh,
one
I thought
was-
like
I
the
was
dark
like-
and the thin were one part
Yeah.
of the battery.
No, this,
I thought-
like Lisa said, it's like there's 2 batteries connected.
I was like, that is clearly
I
not
totally
And see,
makes
again,
sense.
you see at this end, this is the positive end and this is the negative end, right? So it doesn't matter which one you looked at.
Totally
All right.
different
That-
sizes.
That was fun.
Yeah.
I was worried that we might have some vision issues, but, okay, so we know that our electrons are flowing this way. We are told this is north, so this is south, so we know then our electric field needs to be going toward the south end. So now, if I have it like this, they're forced up, yeah,
What way is your thumb pointing?
this way. So it's this.
That's nice.
So it's forced up. So then we can say, and it's not out of the page, so we're going to say north. Because you only say like out of the page or into the page if it's going out or in, but this one was going north. Or yeah.
When it's like flat, though, isn't it page?
Because we said north when they go to the north pole of the magnet.
No. North like as a direction.
You get this. If it was north, shouldn't you get like that?
That would be what? Okay, so here's, it's like going, if I'm pointing my thumb is like going east. Okay? And then here, and then it's going up. Oh, I see what you guys are saying.
Your hand's flat.
So I guess you could look at it as being your thumb is going east. The magnetic field then would be coming like out of the page if you're doing it like if this is kind of coming like out of the page. So it's like your fingers are coming out of the page, and then this would be north because then it would be northeast out.
Would be wrong if we said up.
Like, see what this is, do it on the page.
Yeah, it would be better to